Cool. So now that we're at the start of week 5 of the quarter, figured to give a little bit of a roadmap. So far we've seen multitask learning and transfer learning basics, and then we covered some of the core meta-learning algorithms, and last week we covered core unsupervised pre-training algorithms. And really at this point we'll start to dive into slightly more advanced topics. And in particular this week we're going to focus on 2 different advanced meta-learning topics. Today we're going to be talking about task construction and some challenges that can come up and also some opportunities for constructing tasks in different ways. And on Wednesday, we'll be talking about large-scale meta-optimization and ways that you can do things at a larger scale, basically. And then next week, we'll be talking about some Bayesian meta-learning ideas, including actually a bit of a kind of crash course on variational inference, which I think should be useful for at least either as a refresher for some of you, but also for other people, something that's really useful to know about if you aren't familiar with it already. Awesome. So today we're going to be talking about task construction, and really the question of the day will be, how should we define tasks for meta-learning in order to get good performance? And so this is going to cover both a problem that can arise in meta-learning, which is often referred to as memorization, and it happens when tasks are constructed in a particular way. And then we'll also talk about not just a problem, but also an interesting opportunity of trying to construct tasks from unlabeled data and augment the set of tasks that you have available. The first part of the lecture will be covered in homework 4. Homework 4 is optional, but if you do choose to do that, then a lot of the stuff that we'll talk about in the first half of the lecture is quite relevant for that. And so the goals for the end of the lecture is to understand when memorization can happen in meta-learning and also understand techniques for constructing tasks automatically. Awesome. So first let's recap a little bit of what we've covered so far. And in particular, I mentioned trying to clarify some of the terminology. So this is the terminology that we've been using in class or in all the lectures, where essentially we have a set of tasks, we have a set of meta-training tasks and a set of meta-testing tasks, and everything in the green boxes on the left is a training data set or a support set per task, and everything in the red box is what we use to measure generalization, and this is referred to often as the test set for that task or the query set for that task. And one thing that we noted was that you can we're actually using these test sets on the top during the meta-training process. So we're sort of training on the test set, but we're still evaluating on something that is completely new, which are these new held out meta-test tasks. Now, one clarification and one point of confusion that came up is sometimes in the homeworks, we were referring to meta-training and meta-test as sometimes being referred to as train and test. This is really confusing and ambiguous, and so it's something that we'll try to fix in future iterations of the course. And to somewhat try to make it less ambiguous in the homework, the train sets were referred to support and query, and so that was differentiating it from train and test, but it was also already still somewhat confusing, and hopefully this clarification helps resolve some confusion there. Awesome. And then beyond the setup, we've talked about black box meta-learning, where the key idea is to parameterize a learner as a neural network. And this network is the inner loop of the meta-learning process. It learns from a few examples. Sometimes this learning process is also called in-context learning, and you'll see that terminology used a lot in the NLP literature and also used in homework 3. And then when we actually go about training this neural network to learn from these examples, that's the meta-learning process or the outer loop process. The benefits of black box meta-learning is that it's very expressive. This inner loop can represent a wide range of learning procedures, but the downside is that it can be a challenging optimization problem, which you probably saw in homework 1. We've also covered optimization-based meta-learning that embeds gradient descent inside the meta-learning process. This incorporates the structure of optimization that we know and love, but it requires a second-order optimization. And so in homework 2, you may have found that second-order optimization can make it slower or a little bit harder to deal with. And then lastly, we also talked about non-parametric meta-learning, where you create an embedding of all of your examples and then do some form of nearest neighbors to compare the test example with your training examples and output the label that you think of the example that you think you're closest to. Great. And so as you are hopefully seeing in homework 2, this can be easier to optimize and computationally faster, but it is largely restricted to classification problems. And then lastly, in terms of the task construction process, what we've seen in the first 2 homeworks is kind of n-way classification problem. But the same ideas can be applied to having different tasks correspond to different regions or corresponding to different robotics tasks. And in kind of all of these settings, you need to construct a set of tasks using a significant amount of labeled data. Great. So now let's talk a little bit about kind of the main topic of this lecture, which is memorization and unsupervised meta-learning. And so I'd like to start this off with a bit of a thought exercise for you. And in particular, this is kind of one picture of a black box meta-learner that takes as input a training data set and a test input and gives you a predicted label for that test input. And the thought exercise is when you have, you train this on a set of tasks. Each task is indexed by I. And one thing you could consider doing is passing in the task index, a one-hot identifier of the task index, into your black box meta-learner. And my thought exercise first is when you pass in both the trained data set and the task identifier, what would happen during meta training? Yeah?
The model learns to associate the training set memory.
So the response was it might learn to associate the task identifier and the training data set and memorize it. What is it?
Just so like remember the.
Another answer?
I mean, all of that stuff is really complicated. One topic is not. So it might over-rely on one.
Yeah, so the examples that show up in the training data set are pretty complicated, whereas this one-hot vector is not very complicated. And so what it might do is it might learn to rely on the task identifier rather than using the training data. And during meta training, this probably isn't a problem. Basically, it might just learn to rely on this task identifier instead. Basically, the task identifier and the training data are redundant. They both encode information about the task. And then my next question is, if it does start to rely on this task identifier, what would happen at meta test time if you pass in a new training data set and a task identifier for a new task? And so this would be a one-hot vector for a one-hot vector that's different than the one-hot vectors that it saw during training, particularly during meta training. Yeah?
Performance would probably be really terrible because it would try to rely on the task identifier again, but since it's a one-hot representation, it has no correspondence with any of the ones it's seen before.
Yeah, so the answer was the performance would probably be pretty terrible because the one-hot vector for the new task is different from any of the one-hot vectors it saw before, and because it's relying on that, it wouldn't be able to actually perform the new task. So it won't, in sum, it won't generalize to the new task. So, okay, this seems like kind of an initial thought exercise. Now, a second thought exercise, what if instead of giving it a one-hot vector, what if we gave it a paragraph that describes what it should do, like how to do the task or what the task is? Does anyone have thoughts on what would happen during meta training and perhaps also during meta testing?
I mean, since I'm dealing with it, it depends on how, it's going to depend on what thing is going to be more complicated and messy, where the algorithm is going to decide to like take the data. So like, if the paragraph is way bigger than the task, the observation.
Yeah, so the paragraph is going to be a lot more complicated than a one-hot vector. And what the network decides to use will depend on how complicated the paragraph is versus how complicated it is to discern the task from the training data. And so it depends on basically whether it's easier for the neural network to use the description or to use the data. And similarly, if in terms of generalization to new tasks, in some ways it depends on what it decides to use during meta training, and also the structure of that paragraph. It may be that it can actually generalize to the new task using the paragraph description if it has kind of learned sufficiently general representations of natural language text. But it could also be that maybe it sees a new word in the new paragraph or the new task that it hasn't seen before, and it can't interpret what the goal of the task is. Okay, so these are two initial thought exercises, and to start kind of getting you thinking a little bit. Now, the key problem that arises in both of these thought exercises is that the model can minimize the meta-training loss without actually looking at the support set or without actually looking at the training data for your task. And this means that it won't actually necessarily learn a learning procedure that relies on that training data. And so if we go back to how we've been constructing tasks for few-shot classification problems, typically we'll do it something like this, where for task 1, we sample some images, we assign some labels kind of in an arbitrary or random way, but we make sure that the labels are consistent between training and test, or between support and query. And likewise, for the second task, we'll again sample a new set of labels, arbitrarily assign labels to images, and we'll do this for each of the tasks. And one thing that you can note here is when we do this, across different tasks, the piano class, for example, has a label of 4 for the first task, and it has a label of 3 for the third task. And so this means that when we randomly assign class labels to image classes for each task, the tasks are mutually exclusive. And what I mean by that is there doesn't exist a single neural network that can classify the images in task 1 and the images in class 3. Because you have fundamentally a different label being assigned to the same image class. And as a result of the fact that the tasks are mutually exclusive, it means that in order to actually solve and be able to minimize the meta-training loss, they have to actually use the training data. They have to look at the assignment of labels to images in the training data in order to accurately make predictions on the test sets or the query sets. Cool. Everyone following? Okay. Now, the third thought exercise is, what if we assigned labels in a way that was consistent across tasks? And so in particular, say that we assigned the labels like this. And what I mean by consistent is I mean that the image class of piano or the image class of this breed of dog is always going to be the same across all of the tasks. And so this means that the tasks are non-mutually exclusive, and a single function could solve all of the tasks. And so then my question to you is what would happen in this case? Yeah? Yeah, so just like the previous thought exercises, you would still memorize and you wouldn't actually learn how to learn because you can just learn a single function that classifies rather than relying on the support data. Yeah?
Wouldn't it also be the case that for your query examples, you would have seen it like in the support set because would that result in a problem?
You're saying that you're asking, is it also a problem that for the query images you would have seen them in the support?
Yeah, so for different tasks, would that result in an issue for this specific setting? So the dog image, for example, for task 1, it is in the query set, and then for task 3, it's is in the support set?
Got it. So the question is, in some cases, like the same image is in the query set in for some tasks and in the support set for other tasks. And also this class is appearing multiple times. That's actually not a problem. And I would guess that for most of you, the way that you implemented homework 1, you may have actually had images appear sometimes in the support set and sometimes in the query set. You can get a little bit more out of your data if you have it be allowed to be appearing in either the support set or the query set. Cool. So in this case, the network can just learn to classify the inputs irrespective of the training set. And so in particular, what can happen is that when you train a black box meta-learner, it can basically learn to just ignore this input and just classify based off of the X test, based on the query example. And likewise, even for an optimization-based meta-learner, it could also learn to basically ignore this and primarily rely on just the initial network in order to make predictions. It's a little bit more difficult in this case because it actually has to learn how to ignore the gradient descent step, but it can also figure out how to do that. Yeah.
There's also another problem, right, where we are assigning multiple images like pianos, and there was another thing which was assigned the same index. The index actually holds multiple semantics together, so we need a higher capacity to memorize this, or
yeah, that's a great question. So the question was, one thing you may have noted here is that there are actually multiple meanings. Like even though the labeling is consistent, there are multiple meanings for a given label. So like 4 means both a carousel and a piano, for example. And so this does mean that the network does need to have enough capacity in order to be able to kind of lump those concepts together. And we'll actually start to see some experiments, and this may also start to hint towards some solutions to the problem. Cool. So it can ignore things, and if you actually run meta training on this exact example that I gave you, and then evaluate it on examples from new classes, its ability to learn from a new data set, the accuracy goes to around 7.8% or 50% in these 2 different problems. And this is for the mammal algorithm, so it's even something that has to use a gradient descent step. And so it's actually running fine-tuning at test time. It's just not giving you a very accurate model on these new classes. If you did evaluate it on the classes it saw during training, it would be able to give you good accuracy because those are classes that it saw. Cool. So then there's this question of, okay, we're not shuffling the labels. And when we don't shuffle the labels, this is a big problem. Our performance really plummets. But is this actually a problem in practice? And for image classification, we can just shuffle the labels. It's something that we can do. It's also very easy to do. And so it's not really a problem for image classification problems. Like I mentioned, it's also not a problem if you see the same image classes as what you saw during meta training. But it is actually going to be a problem in some cases if you want to be able to adapt with data for new tasks, and if you aren't looking at problems exactly like some of the few-shot classification problems that we saw before and that we've seen in the homeworks. So let's look at a few examples where this may actually be a problem. So this first example is a robotics task. So say we want different tasks are going to correspond to manipulating objects in different ways. So one task might be to close the drawer. Another task might be to pick up the hammer and hit a nail. Another task might be to stack these 2 blocks. This seems like a very natural task distribution for a meta-learning system. And maybe kind of the new task, the meta-test task, is to close the box. Now, this is a case where this can be a problem. It can be a problem in a couple different scenarios. One is that if you're doing this from image observations, the system can just look at the initial image, see what's in the initial image. If it sees that there is an open drawer in the initial image, then the task is to close the drawer. Or if it sees that there is a hammer in front of a nail, then the task must be to hammer the nail. And so that's one scenario where it doesn't actually have to meta-learn in order to minimize the meta-training loss. Another scenario is maybe we want to, maybe we aren't in an image-based setting. Maybe it kind of just gets some waypoints, or maybe the initial image is somewhat ambiguous. We might be in a scenario where maybe we want to tell it, like, give it a language description of what the task is, like close the drawer or hammer the hammer. In those cases, if you also give it a task description, which should be helpful, we're giving it more information, that will also make it much harder to generalize to a new task. So this is one example. One more example, let's consider a pose prediction task. So say you want to predict the orientation of an object in an image. And so maybe your meta-training task, you're predicting the orientation of a couch. In another case, you're predicting the orientation of, I think this is a very old monitor or television. And then at meta-test time, you want to be able to predict the orientation of a chair. This is also a case where you can kind of look at the image, and you don't actually need the meta-training data in order to be able to predict the orientation. But if you give it a new object, it may be ambiguous what the canonical orientation of that object is. And because of that ambiguity, you do want it to actually look at the meta-training set, or sorry, the support set or the training set for that test task in order to actually figure out what the canonical orientation is and how to predict the orientation of the object. Cool. So this is another example where memorization can occur. And in this case, it would memorize the canonical orientations of the objects seen during meta-training, and it would it wouldn't be able to figure out what the canonical orientation of the new objects are, because it didn't actually learn to pay attention to the support set. Cool. So do people agree that this is a problem? Cool, OK. More or less. Now there's the question of whether we can actually do something about this. And so to think about whether we can do something about it, let's try to formalize the problem a little bit more. And in particular, we saw that if the tasks are mutually exclusive, then a single function cannot solve all of the tasks. And this could be due to label shuffling. It could be due to hiding information. And in this setting, the meta-learning process will not memorize, and you should be able to generalize to new tasks. On the flip side, if the tasks are not mutually exclusive, then a single function can solve all the tasks, and it can just ignore the training data. And in this latter case, memorization can occur. And the reason why memorization can occur is that there's actually multiple solutions to the meta-learning problem. There's multiple ways to minimize the meta-training loss function. And in particular, if we view the meta-learning process as taking as input the training data set and the test input and relying on our meta-parameters theta, one solution to the pose example would be to memorize the canonical pose information in your meta-parameters and ignore the support set. And then another solution, which is one that we would often want if we want to generalize, is to carry no information about canonical pose information in theta, and instead try to acquire it from the task training set. And so here are two solutions. And in general, there's actually going to be an entire spectrum of solutions where you could, based on how the information flows. So you could store some information in theta and acquire some information from the support set. And likewise, and basically there's kind of a spectrum of solutions in between these two extremes. Although in practice, you'll probably get either one of these two extremes. Yeah.
When we are doing the training, won't you have like some validation set which has like some objects which are not seen, and like when we are tuning the hyperparameters of the optimization, shouldn't the optimization go towards the another solution part because we have a validation set of trade-off objects?
Yeah, so the question is, if we have a kind of a meta-validation set or a set of validation tasks, we should be able to tell if our model is generalizing to new tasks. And as a result, maybe we can tune the hyperparameters in some way in order to actually encourage it to generalize better. In general, absolutely, you'll see that it won't generalize to validation tasks. The tricky part is, how do you tune the hyperparameters in order to actually get it to generalize versus not generalize? And so you can diagnose this sort of problem with held out validation tasks, but you cannot you can't necessarily solve it. You can maybe try to tweak the learning rate in some way to try to kind of try to get it to do the right thing, but in general, it's tricky to do it purely based on like learning rate or purely based off of like the size of the architecture.
If you do an automatic like Bayesian hyperparameter tuner, it won't be able to fix this problem, like fuzzy or something.
So the question was, if you kind of pass this into a hyperparameter optimizer, would it be able to fix this problem? And it really depends on the hyperparameters that you expose to the model. And in particular, we're going to need some form of regularization to encourage this to not happen. I guess the other thing that I'll mention is in general, I see this solution happen more than this solution. And I think that that's because acquiring information from detrain can be an imperfect process. You actually have to acquire it from a more complex object. And as a result, oftentimes you can actually get a slightly lower meta-training error with this solution than with this solution. Cool. So if we view it as, if we view this kind of from the standpoint of how the information is flowing, we might be able to think about trying to control that information flow. And in particular, we think of the meta-training process as something like this. And there's like a number of there's basically 3 objects that you can use to get a prediction. There's information in theta, information in dtrain, and information in xtest. And we're primarily going to focus on the first 2, information in theta and information in dtrain. And when we think about like how dtrain and theta affect the corresponding prediction, we can try to think about basically encouraging it to use this information more so than using the information from theta. Now, one thing that would be nice to do is if we could try to maximize the mutual information between the support set and the prediction. If we could maximize that mutual information, I think that would give us exactly what we want, because then we'd be encouraging it to use information from dtrain. And this wouldn't in any way be competing with optimizing the meta-training loss. But unfortunately, optimizing mutual information, like actually estimating this and optimizing it, is pretty difficult. And so instead, what we're going to try to do is try to minimize the information coming from theta. And that's something that's easier to do. Of course, if we only minimize the information coming from theta, then we won't be able to do things well. Yeah?
Can you clarify what you mean by maximizing mutual information between the support?
Yeah, so the question is, can I clarify what I mean between maximizing the mutual information between the support set and the query set prediction? I guess I mean that in the kind of mathematical sense. So if you view these as 2 different random variables, then you can define the mutual information between 2 variables like A and B as, I guess there's a number of different ways to define it, but like one way to define it is in terms of like the entropy of 2 different variables. Another way to define it is the KL divergence between the joint distribution and the joint distribution and the kind of the product of the marginals. And basically, mutual information is going to be telling you like how interrelated are these two random variables? And if they're completely independent, then they have zero mutual information. And by actually trying to maximize that mutual information, it means that we want y to actually change when dtrain changes. And so if we're able to maximize that quantity, that means that when we change dtrain, y will actually change, and that means that it will actually rely on dtrain rather than completely ignoring it. Yeah?
Is theta kind of like the out-of-plane information for the task in general, and then we're trying to like kind of fine-tune with the training data set?
Sorry, can you? I missed like one word in the first part. Is theta the?
So in the initial lectures, we have a like plate notation, right? Where the theta kind of the phi thing, which has like general information about shared tasks, and then we're like trying to fine-tune with the training data set that we have.
Yeah, so you can think of theta as the shared information. Although in this case, I'm actually just referring to it as the meta parameters, like the parameters that you're optimizing during the meta training process. But yeah, when you think of it as a random variable, sometimes it can be helpful to think of it also in terms of the kind of the shared structure. But here, really, I'm referring to it as the meta training parameters. Cool. So it'd be awesome if we could maximize the mutual information, because then we'd be telling it to rely on dtrain to basically make different predictions for different dtrain. Unfortunately, it's difficult to optimize that quantity. And so instead, what we can try to do is to minimize information coming from theta. And of course, we can't only minimize information coming from theta, because if we did that, then we wouldn't store any information in theta at all, and we then wouldn't be able to do very well. We'd just basically be learning from scratch in that case. And so instead, what we're going to do is we're going to try to minimize the information in theta and also minimize the meta-training loss. And we'll need to balance those two terms such that we're getting a kind of a meta-training loss that we're happy with, while also trying to minimize the information in theta as much as we can. Now, the way that we actually go about doing this relies on kind of some knowledge of what's called an information bottleneck. And we'll actually be covering information bottlenecks on Monday next week. So I don't want to go too much into it right now. But the intuition behind what we'll be doing is we're essentially just going to be adding noise to theta. And when you add noise to theta, you're removing information from what's in theta. You're increasing the entropy of that random variable. And so by doing so, by basically trying to minimize training loss under a noisy, minimize meta-training loss under a noisy version of theta, that means that you're going to be trying to basically telling it to be able to do meta-training with less information in theta as compared to previously. And so this kind of specific equation for what this will look like is you have your meta-training loss function that I've just written out as L here. And the way that you write out a typical information bottleneck is the KL divergence between your distribution over theta and some prior distribution, which is just a kind of a standard Gaussian distribution. And the reason why this corresponds to adding noise is Q is going to be a Gaussian distribution with a mean of theta and a variance of kind of a diagonal variance. And so Gaussian distribution basically is a sample from that Gaussian distribution. It corresponds to adding noise to the mean of the Gaussian distribution, and hence why you can think about it as adding noise to the variable. And so essentially what this is going to do is it's going to try to place precedence on using information from the support set over using information from theta, because using information from theta is now going to be harder, because now you have to use information from theta after noise has been added to theta. And you resample the noise every time you use the meta parameters theta. Yeah?
So you want theta to contain the shared structure between the task, but not the task identifier. You won't forget the task. Way to identify task, so can't be like actually put like a adversarial clause which like predicts the task identifier from theta and then minimize it. So let's say for your sofa example, you can actually try to predict the label sofa from like, because when we are generating the tasks, we know which like object they're coming from, right? So you can have a loss term that tries to disentangle like the information.
Yeah, it's an interesting idea. So here we're just kind of blindly trying to add noise and reduce information from theta. Maybe we can try to do it in a slightly more targeted way by trying to kind of explicitly say you shouldn't be able to predict the memorized information from theta. You were suggesting that you shouldn't be able to predict the kind of the task identifier, which wouldn't quite work. The tricky part is that like in the pose example, the memorized information basically corresponds to the canonical orientation of each of the meta-training objects, and it has it for all the objects. And well, I don't see any way to try to hit that information in a targeted way, but we could also discuss it, and if any good ideas come out of it, then it could be interesting to explore. Yeah?
Couldn't you pass your support set through the meta parameters and then try to predict the task identifier for that? And that would restrict your information about the task memorization in the meta parameters.
So you're saying that, are you saying to like erase this arrow and have an arrow from here to here? Or are you saying to add an arrow from dtrain to theta? And then?
I'm just trying to, so one possible initiation of what my colleague said would be to take your support data point and pass it through the meta parameters, and then on the activations, learn a neural network that will try to predict the task identifier, and that would restrict your stored information about tasks in the meta parameters.
Yeah, so you could try to have something like on top of the activations that basically has it such that it can't predict the task identifier from that. The tricky part is you don't want to restrict information from dtrain in any way. You only want to restrict it from theta and not from dtrain. But maybe we can also discuss it a little bit more after class. Cool. Now, this regularizer that adds noise to weights, it's actually used in other parts of deep learning. It's often referred to as kind of Bayes by Bragg prop, where you're basically imposing a Gaussian distribution on the weights of a neural network. And once you define this regularizer, which is basically just adding noise to the weights, you can really combine it with your favorite meta-learning algorithm, and it's applicable to any of the algorithms that we've talked about in this class. Cool. So how well does this work? So I mentioned that this sort of regularizer is actually, it's been used in kind of standard deep learning. It hasn't actually been that successful in standard deep learning. Usually you can get kind of a few percentage improvement. But if we look at the meta-learning settings, it actually tends to have a more drastic effect. So for example, if you take the omniglot dataset, which you've been working with in your homework, and you remove the label shuffling such that the labels are consistent across tasks, we'll refer to this as non-mutually exclusive omniglot. The original mammal algorithm, in this case, will get very low performance. There's another work that proposed a form of regularization that may actually be somewhat similar to what was suggested, but it also doesn't work very well. Whereas if you do this approach of adding noise to the weights, you're actually able to recover a lot of the performance in comparison to using label shuffling. And similarly, on the pose prediction task, which is more interesting than the omniglot task, it's harder to just shuffle the labels. If you look at the mean squared error between the predicted orientation and the correct orientation, we see that we can get a much lower mean squared error when incorporating this kind of form of meta-regularization. And you see an improvement both with the mammal algorithm as well as an algorithm called conditional neural processes, which are a form of a black box meta-learner. Yeah.
So one thing I was thinking was if we, so currently this algorithm like adds random noise to all of the weights of the network. How does this compare to just like essentially keeping the earlier layers of the network fixed, but then just reinitializing the last layer, like setting up completely random noise? So then you can't really like, so like the algorithm won't want to train like the final prediction task, but it still like learns the features. So it's kind of like the coordinates in that sense.
Yeah.
The
So
question is, so this is adding noise to all the weights. How would this compare to kind of meta-training the earlier layers as normal, but then always reinitializing the last layer? And you'd also do that during meta-training, right? And then fully train the last layer in the inner loop. Yeah. So I think that something like that would, off the top of my head, I think that something like that would work. In general, things like prototypical networks actually often don't suffer from this memorization problem because you're forcing it to do nearest neighbors. It has to use that learning algorithm, and it's much more difficult to kind of memorize like how to map from inputs to labels when you literally have to like do these sorts of nearest neighbor comparisons. And so, given the relation to things like prototypical networks, I would expect that to work, especially for classification. I might have to think about it a little bit more for regression, but I suspect that something like that might work because you're forcing it to learn part of the network from scratch in the inner loop. But I may also need to think about it more to, yeah.
What's the intuition, I guess, between adding noise versus something like dropout, I guess similar thing.
Yeah, so the question is, what's the difference between adding noise versus something like dropout? So in this paper, we actually looked at adding noise to the weights and also adding noise to the activations. And something like dropout is going to be a lot more similar to adding noise to the activations. And we found that adding noise to the activations actually worked in some cases, but didn't work well in all cases. And so the reason why there's a W here is kind of refers to adding noise to the weights versus adding noise to the activations. And so you can see the activations results in the paper. The part of the challenge with adding noise to the activations or doing something like dropout is it can still, I guess it depends on like which layer you add noise to, but the essentially say you have a neural network that is making predictions about a corresponding input. And then say you kind of decide to like, I don't know, try to add noise here, or maybe you could even just add noise in, let's say, okay, so say you add noise right here. You're basically just trying to like minimize and have less information here. But what the network can do is, especially for classification tasks, the amount of information in a label is very small. If you're doing like 10-way classification, then it's just log 10. And so if you're trying to minimize information in the activations, it can actually minimize information just by like basically stuffing the label here. And that's very, very little information that it needs to store. And that's actually less information than what it needs to memorize. And so I don't know if that was the most clear explanation, but basically it's the place where it's memorizing is really in the weights of this neural network and not in the activations of this neural network. But the short answer is it works a lot better on the weights than the activations. Cool. And then, yeah, I guess we don't have dropout in these comparisons, but you could also just try applying things like weight decay or a version of Bayes by Brack prop, and we see that it works much better. With the kind of regularization that we've talked about. Cool. Now, one thing that I'd like to briefly mention for people who are more theoretically inclined and want to dig a little bit deeper into this is this form of regularizer. We could ask, like, we've seen in practice it really improves generalization a lot, but does it actually do so kind of in a more provable sense? And there's a way to kind of basically derive a generalization bound for this approach. And it looks rather complicated, something like this. But basically what this amounts to is we're trying to bound the generalization error, or basically how well will this meta-training algorithm generalize to new meta-test tasks. So that's the left-hand side. The right-hand side is a bound on the error. And so this corresponds to the error on the meta-training set plus the generalization gap. And this term in the generalization gap is exactly the meta-regularization that we're applying when we add noise to the weights. So really the gist of this is that you can actually theoretically show that you can bound the generalization error and actually improve generalization, or at least you're bound on the generalization by using this form of regularization. Cool. So to summarize the memorization problem, we talked about this, basically this form of overfitting in meta-learning where you're memorizing a mapping from X to Y. You're memorizing a function. And basically you're memorizing, the X to Y function rather than actually using the training data, rather than learning to learn. And this is analogous to standard overfitting in supervised learning, where you, instead of memorizing functions, you're memorizing individual training data points. And similarly, you can sort of think of kind of meta-regularization as also being analogous to standard regularization in supervised learning. Although in supervised learning, you're kind of regularizing the hypothesis class, you can also think of this as regularizing the hypothesis class of the meta-learner. And this has a particular interpretation of controlling information flow. And you can view the specific meta-regularization that we talked about as trying to minimize the description length of the meta-parameters. And so these are also somewhat analogous, although, like I briefly mentioned before, we actually see a much more drastic improvement from applying this regularization in some meta-learning problems in comparison to kind of standard regularization in deep learning. Any questions on memorization? Yeah.
What do you mean by description length?
That's a great question. Do I want to go into that? I guess I put it on the slide. So description length is, maybe I shouldn't have put it on the slide. I think I'd rather not go into it now, but happy to talk about it in office hours. And if you're interested in learning more, you can read up on the MDL principle, which is the minimum description length principle, and Kolmogorov complexity. And I guess the gist of it is it's thinking about the length of the program that it takes in order to express a function, the length of the minimum program. Yeah.
Is that essentially just the amount of information that's stored?
Yeah.
Yeah, basically it's a measure of information. Cool. Okay, so we've talked about a problem that comes up if you construct tasks in a certain way, and I'd encourage you to, for those of you that are doing projects along the lines of few-shot meta-learning, I'd encourage yourself to kind of ask yourself if this sort of issue might come up in your project. And if so, you can maybe consider revising your project or think about the regularization techniques that we've talked about, or possibly develop a new regularization technique. Cool, and then the second part of this lecture, I'd like to talk a little bit about another form of task construction, which is unsupervised task construction. And earlier in this lecture, we revisited a few different examples of classification, imitation learning, and land cover classification. And these are all scenarios where we assume that we have labeled data from lots of different tasks. And there might be scenarios where we only have unlabeled data, or maybe we have a mix of unlabeled data and labeled data. Last week, we talked about a class of approaches that can handle the setting where we only have labeled data during pre-training. And we did this with different unsupervised pre-training algorithms like contrastive learning and like masked autoencoders. and we pre-trained a representation and then fine-tuned something on top of that representation. And today we're going to talk about algorithms that are actually end up looking very similar to those previous algorithms, except instead of just running fine-tuning on top of the representation, we're actually going to be doing explicit meta-learning and doing the same kind of few-shot learning that we've seen in algorithms like black box meta-learning and non-parametric methods and so forth. And the general recipe for these algorithms is going to be something like we are given an unlabeled data set, then we will propose tasks from that data set, and then run meta-learning on the tasks that we proposed. And this is going to look a lot like the recipe that we saw for contrastive learning as well, where we are basically constructing tasks using different augmentation functions. Of course, the key step here is this middle step. It's easy to get, well, given unlabeled data is just a given. Running meta-learning is what we've already talked about over the past few weeks. So the big question is, how do we propose tasks? And yeah, our goal will be to try to automatically construct tasks from unlabeled data. Now, I'm curious if anyone has thoughts on, if you were to try to kind of set out some desiderata for a set of tasks, do you have thoughts on what you would want generally that task set to look like? Yeah?
I feel like it depends on the data that we're dealing with, but for the case of images, for example, I think it would be similar to contrastive, as in similar instances should be like the same class, and then I would like to have a diverse like set of labels for my tasks. I don't know.
Yeah, so for image, it's going to depend a bit on the data, definitely. And also it's going to depend a bit on the tasks. So if at meta test time you expect to be doing a 10-way classification task, then the tasks you construct during this process will be different than if you think you're going to be doing like a 1,000-way classification. And so you want to construct things that look similar to what you are going to see at meta test time. You could also imagine doing something similar to contrastive learning. Yeah?
It kind of looks like how you'll do like K-means clustering, like identifying the clusters. So like they should be prominent enough in the data set to be like, to individually be classified as a cluster, and the difference between those clusters or tasks should be like reasonably prominent.
Did you look at the next slide? Yeah, so to repeat the, I guess maybe to summarize, maybe we want the tasks to be something like, kind of like what you get from K-means, to be somewhat distinct from each other, while also being somewhat diverse, I guess. So yeah, what I put on the slides is I think that we really want two key criteria. One is that we want the tasks to be pretty diverse. We want them, and the reason why we want this is that we want them to be able to cover the test tasks that we are likely to see during meta test time. And of course, if you know information about what you're going to see about meta test time, like if it's 10-way versus 1,000-way, you can incorporate that and actually make it less diverse to make it more similar to that. And then the second thing you want is you want it to have some structure. So if you propose completely random tasks, then your meta-learner won't actually be able to learn those tasks with a few examples. And this maybe gets a little bit at the K-means comment a little bit, which is that if you cluster data, kind of intuitively what that's doing is kind of finding the structure underlying the data. And we can try to leverage that structure when during the kind of meta-learning process. Yeah?
Is there a way to formally define covering the test tasks?
Is there a way to formally define covering the test tasks? It's easy to define if you can represent the task distribution in a parametric manner. If there is kind of some parameter underlying the task distribution, then you can kind of say, is this in the support of the distribution? If the tasks are not possible to describe in a parametric manner if they're kind of more non-parametric, like one task is to like pick up a shoe and another task is to push a chair. Like maybe you could parameterize the shape of the chair and the shape of the shoe, but in general, that's something that's much harder to characterize. Cool. So we'll talk about how we might try to recover diverse and structured tasks, both for image data and text data. This is really the main overview slide, and then on the next few slides, we'll basically just go through a few examples for how, and walk through examples for constructing tasks that maybe look like this, and also like how these algorithms are used in practice. The first example will actually be using something a lot like k-means clustering. And in particular, we're going to be doing this with images. And if you just have image observations, it's hard to run clustering on raw pixels. And so what we'll first do is run unsupervised learning in order to get some embedding space, a lower dimensional embedding space. And once we have this lower dimensional embedding space, it's going to be much easier to construct tasks. And in particular, if we want to construct a classification task, then we can find different clusters in this embedding space and define a task as discriminating between examples from those clusters. So for example, one three-way classification task would be to be able to classify between purple examples, green examples, and orange examples. And another task might be to classify between like the red dashed cluster and the yellow dashed cluster. And by running clustering to get these tasks, we're going to get parts of the space that have a little bit more structure. In contrast, if we just randomly kind of sliced like hyperplanes, like decision boundaries through the space, then we may end up kind of getting much less structure because you may get kind of two examples that are very close together, but that actually have different labels. And so in particular, to propose a task, once we have this embedding space, we first sample, if we want to do a two-way classification task, we sample two clusters, so like the red cluster and the blue cluster. We sample two images from those two clusters, so the blue image and the red image. And then that will give us a support set for that task. And then to get a query set, we then sample two additional examples from each of those clusters and get a corresponding query set for that task. And then once we go and try to sample another task, we can simply sample another set of clusters, like the purple cluster and the green cluster. And then if we wanted to sample, these are two-way classification tasks. If we wanted to do an n-way classification task, then we can sample n clusters and discriminate between examples from those n clusters. And you can note that these tasks don't correspond to exactly categorizing different, like, typical image categories, but they still have a lot of structure to them. For example, the first task corresponds to like classifying if something is like a circular shape versus if you have a pair of objects. And the second is maybe classifying wine bottles or maybe bottles of beverages and something that also has a particular kind of shape. Cool. And then once we have defined these tasks, we just run meta-learning on those tasks. So this is one way to get tasks that are fairly diverse and are fairly structured. And the result of this process should be a representation or a meta-learn model that is particularly well suited for downstream few-shot classification tasks. And it should be something that's actually better than the initial representation that we used in step 1. And the reason for that is we're explicitly going to be optimizing for few-shot generalization in these examples and kind of few-shot n-way classification depending on whatever form of n-way classification we set up in step 2. And so there's a few different ways to actually instantiate the different steps here. So the first step, we could use some unsupervised learning methods. This paper is a couple years old, so it's going to use some unsupervised learning methods that are a couple years old, but you could also plug in something more recent as well. clustering to automatically construct tasks for unsupervised meta-learning, or Cactus. And then you can combine this with a meta-learning algorithm that operates on those tasks, like MAML or prototypical networks. And then we can look at some of the results. So we looked at using this approach to construct tasks in combination with both MAML and prototypical networks. And so if you combine Cactus with MAML, this is the result that you get. And we evaluated it on mini ImageNet, which if you give it full labels, you get an accuracy of 62%. If you just do, I guess you can first evaluate a few different unsupervised baselines, which just corresponded to doing k-nearest neighbors, logistic regression, or an MLP on top of the pre-trained representation. And you get few-shot accuracy that's pretty low, in around 30%. You can also do something that uses clustering. And in contrast, if you actually run this approach to construct the tasks and do meta-learning on top of those tasks, you get an accuracy that's much higher, around 51%. And if you use a representation that's a bit better, the deep cluster representation, you actually do even better than that. Yeah?
I'm not sure if I understand. So if you're not giving it labels, we're just saying that the clusters that it creates have like this in cluster A happens to correspond with this label. Is that what it's saying?
Oh, are you specifically referring to this method right here?
Yeah, well, because
Yeah, so basically all four of these methods correspond to different ways of using the unsupervised representation on its own. And basically using different kinds of, like classifiers or something on top of that. Yeah.
So are there labels at test time, meta test time?
Oh, awesome question. Yeah, are there labels at meta test time? Yes, so in this case, there are 25 labeled examples at meta test time. So the meta training set is completely unlabeled, and then at meta test time, you run it the same exact way as kind of normal labeled meta training time, where you are given a very small training data set, in this case of like 25 examples, 5 examples of 5 different classes.
So basically we're just bootstrapping labels at meta train time and...
Yeah, so basically at meta train time, we are kind of creating our own labels, meta training on that, and then at meta test time, we're using real labels. Yeah.
View this process as first you have the unsupervised projection to a low-dimensional space, and then each task is learning a distortion of that space that moves some images closer together and other images farther away. And then if so, can you characterize the kinds of distortions that can be learned via this process? Like there's a kind of a family of allowable transformations, right?
Yeah, so you can definitely view this as like distorting the space in different ways and then learning learning to classify for those different distortions. You're asking, are there ways to kind of characterize the kinds of distortions that can be represented?
Yeah, the origin of my question is it seems like the adaptability of this depends a lot on the initial unsupervised clustering. Like, you really just transferred a lot of the burden to that step. And if it produces clusters that don't correspond to all of your meta-test tasks, you're going to have a hard time. And so then it seems like it's limited by like, well, how much can you distort or change the space after it's been constructed by that process?
Yeah, absolutely. So it's going to rely a lot on the initial clustering. And I guess I should clarify that we, in this method, you cluster more than once. And you could, if I remember correctly, before clustering more than like each time, we scaled, and I think we like kind of applied some kind of random scaling to the embedding, and that was one way to distort it. You could also imagine fancier ways to distort the space as well. You could also run it you could also have multiple pre-trained representations, and presumably they'll have different things that they pick up on or different high-level features, and that may give you even more diverse tasks. And so this really connects to like the diversity of tasks that you get, and I suspect that in general, it seems like it's actually able to learn pretty diverse tasks that seem to cover things pretty well, especially given that the gap here is only like a 9% gap between supervised, but there's probably also a lot of room for improvement. And these were results with MAML and mini ImageNet 5-way 5-shot, but it also, you kind of see a similar trend with different embedding methods, with different data sets, and also with prototypical networks. Prototypical networks did underperform in some cases, but in general, they're both able to do pretty well. Cool. So that was one way to construct tasks. And coming back to some of what we saw with contrastive learning, you can also construct tasks in a very similar way to what we saw with contrastive learning. So for image data in particular, we know that an image label won't change if you apply certain transformations, like if you drop out some of the pixels or translate the image a little bit or reflect the image. And so if you take Omniglot and you apply a transform like this, or if you kind of flip a mini ImageNet image, the underlying categorization of the image won't change. And so we can use this to construct tasks. So we can construct tasks in the same exact way as what we saw in contrastive learning, where we first randomly sample some images, assign a label to those images, and then for each of those images, we also augment those images in some way, and then assign the same label to those. And then the first image set becomes our support set, and the second becomes our query set. And you could also augment in a different way for your support set as well, if you didn't want to use the original images. And so in practice, you can use whatever you know about the image domain. So for Omniglot, you would use something like translation and pixel dropout. You wouldn't want to flip the image, because that may actually flip the category label of that character. Whereas for mini ImageNet, you would probably do things like flipping. And so they use auto augment here, which corresponds to a number of different transformations. And if you use this approach for task construction, it gets really strong Omniglot performance. In particular, the performance is kind of in the 80s to 90s on Omniglot in many cases. And in the 5-shot setting, this actually gets pretty close to a fully supervised baseline on Omniglot. And this makes sense because we know a lot about the structure of Omniglot images. We have a lot of domain knowledge about that. Whereas for mini ImageNet, it ends up doing somewhat similarly to the clustering approach that we talked about before. And in some cases, it's kind of slightly underperforms that approach. And that also makes sense. We have, I think, a little bit less domain knowledge about the kind of transformations that will affect natural images. Cool. So those were a couple examples with images and how to construct images how to construct tasks when you have unlabeled images. You can also apply the same recipe with text as well, with a different task construction technique. One option which we've seen before is to formulate a language modeling problem, where a sequence, the support set is a sequence of characters, and the query set is the following sequence of characters. And we've seen this kind of example where the inner loop of the meta-learning process kind of goes through each of these examples. You might have these examples as your support set and these examples as your query set. And you have different tasks like translating between languages, math problems, or spelling correction. So this is an example, a way to construct meta-training tasks with just purely unlabeled text. But we might not want to use this option in all cases. For example, it may be harder to combine with optimization-based meta-learning. And it's also not necessarily the best suited for kind of simple binary classification tasks. The second option, which is basically the kind of other form of generative pre-training we talked about, is to use masked language modeling. And the tasks here will just correspond to masking different words. And concretely, the way that you can do this is for a given task, sample a set of unique words, of n unique words, and assign each of those words a unique ID. So for example, you could sample the word democratic and the word capital and assign an ID of 1 to democratic, an ID of 2 to capital. And then you can sample sentences with one of those two words and mask out the word. And then the task is to classify which word was masked out. And so this is going to give you an n-way classification problem if you sample n words, because you'll basically be given, okay, for these n words, which of those words corresponds to the masked out word. And this allows you to construct kind of text classification problems without actually having access to any labeled text data. And so kind of concretely, for the democratic and capital example, we can have a support set that looks like this, where M corresponds to the masked out word. The sentence corresponds to the input. The class corresponds to the label. And we have 2 examples from class 1 and 2 examples from class 2. And then the query will correspond to a new sentence that also has a word masked out. And you need to be able to predict whether or not the label is 1 or 2, or basically whether or not the word is democratic or capital. Cool. So with this kind of approach, you can apply it either in a fully unsupervised way, or you could actually, and really with the other approaches too, you can combine it with some supervised tasks if you have some tasks available. And so here are some kind of what the results look like if you either apply it in a fully unsupervised way, or everything on kind of the right-hand side of the table is if you is a kind of a more semi-supervised or supervised approach. BERT corresponds to kind of what we talked about last week with standard self-supervised learning. SMLMT is the proposed unsupervised approach. Multitask BERT corresponds to multitask learning and fine-tuning on the supervised tasks. There's also an optimization-based meta-learner that's applied only to the supervised tasks, as well as a hybrid method that does meta-learning on the proposed tasks and the supervised tasks. So this is more of like a semi-supervised meta-learning approach. And what we see is by incorporating these tasks generated from the unlabeled data, it's able to do significantly better than only using the labeled data, and also only using the labeled data both for just multitask learning and also for meta-learning. And also we see that for each of these different text classification problems, in many cases this is able to, or in some cases this is able to outperform like a BERT-based pre-training. Cool, this is already a lot of results, but if you want more results, there's kind of more in the paper that's linked. Cool, so in the second part of this lecture, we talked about kind of this form of unsupervised pre-training. It ends up looking a lot like the unsupervised pre-training that we talked about last week, where we saw masked language modeling, we saw autoregressive language modeling, we saw like generating tasks from augmentations. It has this kind of recipe of given an unlabeled data set, propose tasks with these different techniques, and then run meta-learning on it. And really the key difference between these methods and the ones that we saw last week is that we're actually going to be explicitly running meta-learning and using kind of the meta-learner to perform few-shot learning, rather than just doing kind of fine-tuning on top of this on top of some pre-trained representation. And we also covered a few different ways to propose tasks that have been suggested in prior work, which includes classifying between augmented images and different image instances, and like classifying a masked word. Cool. Any questions on, yeah?
So if you have a large number of like shorts, instead of like a few short, would it happen that like the self-supervised pre-training approach overtakes the meta-learning based approach? Representations, and given enough data, it would be able to generalize to the new class.
Given enough test task data, or given like give enough data on the meta test task?
Yeah.
Yeah, so the question is, if you have enough meta test data, would kind of the unsupervised pre-training methods that fine-tune the representation start to outperform what we've talked about? And yeah, the answer is yes. So these kind of approaches are really going to shine if you're in a few-shot regime at meta test time, because they're explicitly optimizing for few-shot learning. And the settings in which unsupervised pre-training are going to do well are settings where you have a bit more data of your target task. Because you don't need to explicitly optimize for few-shot learning. You can simply fine-tune with a reasonable starting point.
The previous method is that actually in the few shots we don't have a mask word, right? So is it able to handle like a sentence without a mask, and because all the training it knows a sentence with a mask?
Yeah, this is a great question. So all of these tasks, it's a good observation. So all of these tasks, like you see this M token, this mask token in the sentences, and at test time, you often won't have mask tokens. And so I think that's part of the reason why this is particularly well suited as a semi-supervised approach, more so than an unsupervised approach. I think that if you really kind of go through these numbers carefully, it'd be nice if there was like a bar plot, but if you go through them quickly or more thoroughly, you'll see that the semi-supervised approach is more performant. And I suspect that this is because there's a bit more of a distribution shift between the unlabeled tasks and the labeled tasks.
Actually better, like our disaster unsupervised is better than the semi-supervised.
Yeah, so there's one task where unsupervised is actually better than all of the approaches that use labeled data. I'm not sure exactly why that's the case. I'd have to kind of look at the paper a little bit more closely, but yeah, it's kind of an interesting finding. Awesome. Cool. So that's it for today.